So in today's video, we're going to go ahead and discuss the second derivative test. And previously we discussed points of inflection and concavity, and now we're going to actually apply these concepts in order to actually use the second derivative test to determine global or relative extrema. And so let's go ahead and do that. So the second derivative test essentially tells us that if we have f, which is a twice differentiable function, right? And so twice differentiable means that the second derivative exists. So let me just say that f double prime and f prime both exist. These both have to exist. Then, and also that we have f prime of c equal to 0 for some c, right? So we have a twice differentiable function with a critical point, right? So a point where, or with a stationary point, at least one stationary point. Then if one of the following three hold, then we can actually use the second derivative test. So essentially, we just have two conditions we need to adhere to over here. We need, first of all, a twice differentiable function, and we need to have at least one critical point. And so, if f double prime of c is greater than 0, so if our second derivative is positive at c, then this tells us that we have a relative minimum at c. And keep in mind, at c, we are stationary. So our first derivative is 0, and our second derivative is positive. That tells us that we have a relative minimum. In a moment, we're going to look at the graphical intuition of this. If the second derivative of c is less than 0, so if our second derivative is negative at c, then this tells us that we have a relative maximum at x equals c. So if our first derivative is equal to 0 and our second derivative is negative, then we have a relative maximum at x equals c. And we can do different tests to determine whether it's a global maximum or a global minimum, but we don't really care about that for the time being. And finally, if f double prime of c is equal to 0, then we simply say that the test is inconclusive. We need more information. We can't determine it just by using the second derivative test. And so yeah, essentially, if we have these two conditions met, we have a twice differentiable function with a critical point, then we can check to see whether that critical point is a relative minimum or a maximum using the second derivative test. And so this is kind of the graphical intuition behind why this works. We said that if f double prime is greater than 0, then we are concave up, right? So here we are concave up. In this particular example, we're concave up. And so that tells us that f double prime is going to be greater than 0. And if we pick this particular point right over here where we have a horizontal tangent line, so over here f prime is equal to 0, right, because we have a horizontal tangent, and we're concave up, then we're going to have a relative minimum, right? Because the only way for it to hold, for us to have a horizontal tangent line, or for us to have a critical or stationary point, and for the graph to be concave up, is if we have a relative minimum. So here we would have a relative minimum. And then over here, if we look at this other example, here we are concave down, right? Because our graph is opening up downwards. We're concave down, and we previously established that whenever we're concave down, then our second derivative is going to be less than 0, right? Our second derivative is negative. And not only that, if we pick this point over here, right, this looks to be a critical point. We have a horizontal tangent. We know that f prime is equal to 0 at this point over here. And so essentially, the only way for us to have our graph concave down and for us to have a horizontal tangent at this particular point is if this point is a relative maximum. So let me actually go ahead and write that over here. This is going to be a relative maximum. So now let's go ahead and do a couple of examples. So here we have f, which is a twice differentiable function with f of 2 equals 3, with f prime of 2 equals 0, and f double prime of 2 equals to 7. And so what we want to do is we want to see what's happening at the point 2, 3. So at 2, 3, right, because we know we have that point, f of 2 is equal to 3, we need to think a little bit about what's happening over here. So first of all, we established that it's a twice differentiable function. So we've met this first condition over here. We've determined that it is a twice differentiable function. And the next thing we need to take a look at is whether or not f prime of our point, or whether or not we have a critical point, right? And it seems that we do. We have this point over here. We have the point f prime of 2 equals to 0, right? So at x equals 2, we have a stationary point. And so if we go over here, then we can go ahead and mark off the second condition. And finally, we have, so now we know actually that we can even use the second derivative test because we're twice differentiable and we have a critical point. And so now we just need to see whether the second derivative test will actually give us a result. So over here we have f double prime of 2 equals to 7. Of course, 7 is not equal to 0, so our test is not inconclusive. And 7 is, as a matter of fact, greater than 0. And so that tells us that at this particular point, f double prime is going to be greater than 0. And so this tells us, as a result, that, let me actually write it over here. This tells us that at the point 2 comma 3, according to the second derivative test, if you want to go back to it, we're going to have a relative minimum, right? And we saw the graphical intuition, we know why this makes sense, and we know mathematically, kind of connecting concavity and inflection points, why all of this works. Or not really inflection points, more so stationary points. And then over here we have another example. Let g be a twice differentiable function with g of negative 1 equals 5, g prime of negative 1 equals 0, and g double prime of negative 1 is also equal to 0. So we are twice differentiable, right? So we can actually check off that condition. And we have a critical point at negative 1. G prime of negative 1 is equal to 0, so that is a critical point. And we have the point negative 1 comma 5. That's the point that we're testing out. But when we look at the second derivative, we get that g double prime is equal to 0. G double prime of negative 1 is equal to 0. And so this tells us that we may have an inflection point. Why? Well, we know that inflection points are points at which we change concavity. So I'm going to write that down. We may have an inflection point with a question mark, because at this particular point, g double prime is equal to 0, right? And so an inflection point, we need the second derivative to either be undefined or equal to 0, and we need to change concavity, so we need the second derivative to also change signs. We don't really know whether it changes signs, but we do have the first condition met for an inflection point, so that's why I use the word may over here. We may have an inflection point. But aside from that kind of guess, we don't really have any other information that would support whether or not this is a minimum or a maximum. We don't really know. And so at this point, we can say that the second derivative test is inconclusive. And the reason why is because, again, if we go back to our little sort of chart that we designed over here, we said that if f double prime of c is equal to 0, then our test is inconclusive. We're going to need more information, maybe the graph of the function or the function itself, or we can determine whether, this is a point of inflection using whether the second derivative is positive or negative, or whether it changes signs. And so all of that aside, essentially, the point is we can use the second derivative test when we're given sufficient information in order to determine whether certain points are relative extrema.